In this session, we will have some more discussion on the slope deflection method. So what we have seen so far is that if we are given a structure of this kind, what we do first is we fix all of the coordinates that we consider, or all of the supports that we consider, and this forms the primary structure for the slope deflection method. And we consider fixture moments for all of these individual spans, and then we allow the respective rotations, let's say theta a, theta b, etc., and we then additionally account for the moments which are required or generated because of these unknown rotations. Then we formulate the problem in terms of the unknown rotations, and then we solve it. Now there are situations where from a hand calculation perspective, it is possible to reduce the number of unknowns. So these number of unknowns, or the number of degrees of freedom, that will be determined, that will determine the size of the matrix equation that we will solve, right? Now there are situations, in this case, let's say this end A and end D, these were both the pin supports, right? So we know that MAB after all of these considerations should be 0, and in fact we were using this as one of the equilibrium conditions when we were considering this, right? Similarly, we know that MDC will be 0, right? So the idea of considering different far end conditions allows us to a priori account for the fact that these moments are 0, and the slope deflection equations are adjusted accordingly. Okay, so this basically arises by considering a different primary structure. Okay, so if we were to implement it on a computer, maybe we will not worry about these different primary structures, because there the number of equations to be solved will not be a constraint. But when we have to do quick hand calculations, this kind of methodology can become very handy, because it helps us in reducing the number of unknowns. Although we have to consider a different set of friction moments because the primary structure we are changing, right? Now the original primary structure we considered like this, where both the ends are fixed. Okay, and then we apply the unknown theta a, and when applying this unknown theta a, there is some moment which is required here, and we worked out this comes out to 4 ei by L theta a. And similarly, because of this, there is a moment induced at the other end, which is MBA due to this, and that comes out to 2 ei by L theta b, theta a, right? Now here we were considering situations where the far end is pinned. Okay, so in this case both ends are fixed. Now let us say we are dealing with a situation where this far end B is pinned, right? So we are writing the equation for joint A, right? So in this case the far end is fixed, right? And this is the situation when we are dealing with either a fixed support or an intermediate roller or pin support, right? But if you are dealing with an end pin, it is possible to consider that situation differently. So we call this far end pinned, right? So if we are considering joint A, the far end B is pinned, right? In this case, if we apply a rotation theta A, right, at A, then again we have to consider, we have to apply some moment. But one thing to note here is that since the far end is pinned, the moment induced here will be 0. Okay, so when we were considering far end as fixed, there was a moment which was induced, which was 2 ei by L theta a. But in case when the far end is pinned, regardless of what theta a we induce here by applying some moment, the far end moment or the moment at B will remain 0. Okay, and this relation between m and theta, we can very easily calculate. So this is a determinate structure, right? So we take the beam and we apply a moment m bar. We can use any method. In this case, I think we have used the moment area method, right? So this theta a is just this delta, this is delta BA, or deflection of point B from tangent at A. So theta A can be calculated as delta BA by L, right? And eventually we get theta A as this. So when we reverse this relation, we get MAB due to this is 3 EI by L. So recall that earlier MAB was 4 EI by L when the far end was fixed, right, times theta A. So there should be a theta A here. and MBA is 0 because we are considering that as a pinned end, and earlier BA was 2 EI by L, right? So by incorporating this change in the slope deflection equations, we can reduce the size of the problem especially when we are solving it by hand. Let's consider an example here. So let's say this continuous beam ABC is given, right? So first we say that we solve it by using the usual slope deflection equations, right? So in this case, there will be 3 unknowns, so theta A, theta B, and theta C, right? So we have to basically solve a 3 by 3 system, and let's see. So for primary structure, we fix all of the supports, right? So we consider each of them individually, right? And we get the friction moments as usual. So MFAB and MFBA are coming for AB, and then here, since there is no external load, friction moments are 0. And let's assume that K is equal to EI by L. So we can write the slope deflection equation. So this is for member AB and this is for member BC. So these are the usual equations, right? And this you can check by yourself. And then we will write equilibrium. So one equilibrium equation we are writing at joint A, where moment at A, which is also MAB, should be equal to 0. Then second equation we write at B, which is moment MBA plus MBC equal to 0. And the third we are writing at C, because that is also a pin support. So we are saying MCB equal to 0, right? So basically these 3 equations give us a 3 by 3 system to solve. We can solve it for theta A, theta B, and theta C. And once we have solved for that, we are able to calculate all the moments which are necessary. And then we can draw the free body diagram for individual spans, and then we can combine it to get the overall free body diagram, and consequently we can get the shear force or the bending moment diagrams, right? So this is the regular approach. This involves solving a 3 by 3 system, and of course from a hand calculation perspectives, the calculations are greater. Okay, now let's consider a modified version of the slope deflection equations, where we consider the far pin ends or the end pins to be pin, right? So now the key difference here is that in the primary structure, now we are fixing only the intermediate support, right? So the ends we are considering as pinned. Okay, so the primary structure we have is this and this. Now here again, since BC there is no external load, the fixed end moments are 0. But for this one, for AB, the fixed end moments have to be modified, because now A cannot carry any moment, right? So now there are 2 options for us to calculate this fixed end moment here. One is that so this is basically a propped cantilever type structure, right? So we can analyze the propped cantilever for MFBA, right? So let's say if we use a force method, we have this plus this, but we impose compatibility, we find out R, which is the reaction rate A. And after finding out R, we can find what is MB, which comes out to 3 PL by 16. So MFBA to be used in this system is going to be this, right? So earlier it was PL by 8, which was the usual fixed end moment, but in this case we have to modify that fixed end moment, right? Now another option is that we recognize the fact that when we were using this idea where the moment at left which was applied was 4 EI by L, and in applying this moment, the moment induced at the right end was half of it. Okay, so this half is something which we will come across multiple times later when we do moment distribution method. But this is something called a carryover factor. So basically, if we are dealing with a situation where we apply a moment at a certain joint and the far joint is fixed, the moment which carries to the far end is half of that. Okay, so we start with the usual fixed end system where both ends are fixed, right? And then the moment induced at both ends is PL by 8 and PL by 8. Now, of course, in reality, we want to consider, let's say, joint A to be allowed to rotate, right? So we allow theta A, which is not being allowed in this particular system. What it means is that we apply a PL by 8 moment in the opposite direction. So here it is clockwise, so we apply a here it is counterclockwise in the fixed end moment. So we apply a clockwise moment like this, And if we apply a clockwise moment at A, right, that means we are allowing the theta A which would have actually occurred. In doing so, we are inducing half of it at B. Okay, so half of it in the same direction. So this PL by 8 plus there is one more coming up which is half of PL by 8, right? So the actual MBA will be PL by 8 plus PL by 16. So that comes out to 3 PL by 16, and you can realize that this is same as what we had earlier. So basically this carryover factor type of arrangement also you can use. Okay, so then we consider the modified slope deflection equations. So for MAB we will not write anything because that we are directly considering as 0, so that equation is not needed, right? Similarly MCB, which is MC, is also not considered because that is now directly equal to 0, because in the primary structure we are not fixing either A or C. Okay, now for MBA we have a situation where the far end, which is A, is pinned. Okay, so MBA we will write as MFBA, right? MFBA is the modified one, right? So MFBA is the modified fixed end moment, and then in order to allow theta B, the moment required will be 3 EI by L times theta B. So this is what we saw earlier, that when so basically we have the end B here and the end A here. So when we rotate this by theta B, the moment required here is 3 EI by L times theta B, right? And the carryover and the moment here is actually 0, right? So in inducing this theta B at point B, the moment added at B is 0, right? So that is where there is no theta A term in this, right? So in the usual case, there was a 4 EI by L theta B, right, plus 2 EI by L theta A. In this case, there is no theta A. Similarly for BC, now the far end C is pinned. So for MBC, we will write MFBC. So this will again be the modified one, right? Plus 3 EI by L theta A, and again now in this case there is no theta C, because to the far end nothing is getting transmitted. Okay, so we have now basically MBA, which is this, and MBC, which is this, and the only equilibrium equation we need to solve is this one, right? And when we solve this, we can calculate what is theta B. So here we need to solve only a scalar equation, whereas earlier we were having to solve a 3 by 3 system, right? And once we plug that into the basic equations, we can get MBC and MBA. So of course, I mean, and you can also verify that these come out to be the same. So the advantage, of course, is that this is easier for hand calculations because it reduces the number of equations, right? Now there is one more interesting case for a far end, which in which case the far end is guided fixed, right? So this is a guided fixed support where it is allowed to move vertically up or down, but it is restrained in rotation and restrained in horizontal direction. Okay, so in this type of situation, if we have to induce a rotation theta A at A, we have to apply some moment m bar, right? And this again we can solve. So this m bar comes out, we can find out a relation between m bar and theta A, or ma and theta A. So mab comes out to ei by L times theta A, and in this case there will be a moment which is induced on the other end B, right? So mba is this. Okay, and usually this kind of support will not manifest itself in a physical system, but it is very useful in analyzing systems with symmetry. Okay, so let's have a brief discussion on what are these systems with symmetry. So symmetry basically has two fundamental requirements. One, that system should be symmetric in geometry, and by geometry we say length, the type of supports, the cross section of the area, and material also we are considering here, although it is not strictly a geometric property. And then it should be symmetric in loads. Okay, so we should be able to find a line of symmetry on the structure with respect to which the geometry and the load both are symmetric for the system, right? Or they are mirror image of one side is mirror image of the other. Let's consider a few examples. So if we consider this fixed beam, it is possible to say that if we draw a line which is at L by 2, right? So this line will be the line of symmetry, right? So basically whatever is to the left of the this line of symmetry is a mirror image of whatever is to the right, right? So the support, the load and the geometry, everything is the same. So and in this case, if we were to visualize the deformed image or deformed profile, it is going to be like this, right? So one key characteristic of this line of symmetry is that at line of symmetry the slope of the system has to be 0, right? So if at this point the slope is not 0, which it would mean that immediately to the left and to the right the value of the slopes can be different, right? So 0 slope is a key indicator of a line of symmetry. Okay, of course displacements have to be continuous, that is there. So in this kind of a case where we want 0 slope at line of symmetry, we can replace this by a guided fixed support, right? So this is going to deform like this. So this can move up or down, it will induce some moment, and wherever there is a line of symmetry, it can be replaced with a guided fixed support. Okay. Let's consider one more case here. So in this one we also see that if we draw a line at the center, there is a line of symmetry. So this is the line of symmetry, right? So about this, whatever is to the left is same as to the right. So we can again replace this at this line of symmetry, we can draw a guided fixed support, and instead of analyzing this structure, we analyze this structure, right? Similarly, there can be a portal frame of this kind. In this case also, there is a line of symmetry here, right? There is a line of symmetry here, right? So we can analyze this half structure with the guided support here. Let's look at few cases where there is no line of symmetry. So in this case, everything is fine, but due to this lateral load P, there is no line of symmetry, because in this case the loads are not symmetric about any line, right? Similarly, in this case, everything is fine, but due to this support which is different from this support, there is no line of symmetry, right? In the third case also, the supports and loads are all fine, but the rigidity of the columns are different, and hence there is no line of symmetry. Okay. Now when we are considering systems with symmetry, the friction moments again need to be adjusted. Okay. So just have a couple of quick examples here. So if this system was being analyzed fully, right? So the friction moments we know are going to come like that. This is a standard case. But if we consider a symmetric system, this one, right? So the MAC is not going to change, or MAC and MAB are going to be same, right? So the left one doesn't change, but to calculate what is MCA or MFCA, what we can do is we can take a moment balance about point A, right? And from there we can write MFCA like that. Similarly, if you are dealing with a central support, centrally loaded fixed beam, we know that the friction moments come out to be like that. But if we are interested in analyzing half of it using symmetry, we are putting a force of P by 2 at L by 2 where there is a guided fixed support, right? And again we can do a moment balance about point A, and from where we can calculate MFCA. So in both of them we are doing moment balance about point A because at point C there is no upward force because it is allowed to move in that direction. Okay, let's do a quick example with symmetry also. Let's say this is the beam which we have to analyze. So in this case the kinematic indeterminacy is 2, or there are two unknowns, theta b and theta c. But of course we see that there is a line of symmetry at the mid span of the overall structure, right? And we assume that EI is equal to K, right? So we can analyze half of the structure where at the line of symmetry we have placed a guided fixed support. Okay, so once we do that, this MFAB and MFBA have no effect, they will remain as it is. but this MFBE is again same as MFBC, which comes out to this, but MFAB is what we calculated earlier, it comes out that. So then we can write the modified slope deflection equations. So for AB it is the same, there is no modification, but for BE what we have is, this is the fixed end moment, and this is the moment required when you rotate joint B, right? And again for joint E there is no question of rotation, because we are not considering that as a degree of freedom here, right? So then again MFEB, we write this, this comes with a minus sign, because you recall that one side was this, the other side was this, but if this was plus, this was minus, right? So EI by L and minus EI by L. Okay, and then we can satisfy the equilibrium, let's say at joint B in this case. So from here we can calculate theta B, and once we calculate theta B, we can calculate the other moments, and then basically we can show all of these moments. For half structure we can show, and for the remaining half we can infer. So if this is 15 in this direction, we will have 15 in that direction, and so on, right? So this can be worked out. So like this we see that use of symmetry can help us halving the number of degrees of freedom, right? So if the original structure has x degrees of freedom, the system with symmetry, if it has, can be solved with x by 2 unknowns, right? Similarly, for cases where far end pins are there, again there can be a reduction in the number of degrees of freedom. So that is the advantage of using these modified slope deflection equations along with the modified primary structure, right? So slope deflection equations are changing because we are changing our primary structure.